Good evening, and welcome back to SleepWise. Tonight, we drift into one of the strangest and most beautiful ideas human beings have ever uncovered. The realization that time is not the same everywhere, that space is not merely empty distance, and that the universe is stranger, gentler, and more fluid than it first appears. That may sound like a subject for chalkboards and difficult books, but tonight we will approach it softly. No heavy mathematics, no pressure to keep up, no need to remember every turn. We will simply move slowly and let the shape of the idea reveal itself. Before relativity, most people imagined the world in a way that felt sensible. Time seemed steady. A minute was a minute, whether it passed in a quiet room, on a moving ship, or beneath the stars. Space seemed like a great fixed stage where planets moved, people hurried, and clocks counted their portions of the day. It was an understandable picture, and for a long time it worked beautifully. If you drop a cup, it falls. If you throw a stone, it rises and returns. If the moon circles the earth and the earth circles the sun, there seems to be no urgent reason to question the deeper framework beneath it all. The universe appears orderly, reliable, almost patient. And yet, now and then, nature leaves a loose thread hanging from the fabric, a tiny inconsistency, a question that seems harmless at first, but refuses to disappear. In the story of relativity, that loose thread was light. Light is such a familiar companion that we rarely stop to think about how strange it is. It arrives from the moon, from distant lamps, from the screens we dim before bed, and from stars so far away that their glow began its journey long before any of us were born. It fills a room at once to the eye, but in truth it travels. And it travels faster than anything else in the known universe. If everything moves relative to something else, then what about light? If you run toward a beam of light, should it seem to approach you faster? If you move away from it, should it seem slower? The question sounds childlike in its simplicity, and yet hidden inside it was the beginning of a revolution. Tonight, we begin not with Einstein himself, but with the world he inherited, a world of certainty, regular motion, and invisible assumptions, a world in which time was thought to flow equally for everyone everywhere like a perfect river. As we settle into that older picture, let your thoughts loosen a little. There is nothing to solve here, only a story to follow. And somewhere ahead, as softly as starlight crossing the dark, we will begin to see why the universe did not keep time the way we once imagined. If these quiet journeys help you rest, you can follow SleepWise and share it with someone who might enjoy falling asleep while learning something new. And now, with the night around us and the clockwork universe still gently turning, let us begin. For a long while, the universe seemed content to behave like a great machine. Long before Einstein, Isaac Newton had given the world a picture of motion so clear and powerful that it shaped human thought for centuries. In that picture, space was fixed, Time was universal, and the heavens obeyed laws as dependable as a falling apple. Newton did not invent motion, of course. People had watched objects move since the first stones were thrown and the first boats drifted from shore. But he gathered those familiar patterns into an elegant system. A thing at rest would remain at rest unless disturbed. A thing in motion would continue in motion unless a force altered its path. The same logic that guided a cart on a road could also guide the moon around the earth. There was something comforting in this. It suggested that nature was not random or moody, but intelligible. The world had rules, and those rules held whether one was watching a candle fall from a table or tracing the arc of a planet across the sky. To many minds, it felt like discovering that the universe could be trusted. Within that grand system sat two silent assumptions. The first was that space existed as a kind of invisible stage, vast, unmoving, and the same for everyone. The second was that time flowed evenly everywhere like a perfect current. 1 second here was 1 second there. Noon on Earth and noon on a distant ship were part of the same universal clock. And yet, even in this older world, some questions had already begun to soften the edges of certainty. Galileo, before Newton, had noticed something subtle about motion. If you were below deck on a smooth sailing ship with no windows to the sea, many ordinary events would look exactly as they would on land. A dropped object would fall straight down. A tossed ball would rise and return. A fly would move through the cabin as though nothing unusual were happening. This was an important thought. It meant that steady motion could hide itself. There was no simple experiment performed entirely inside that smoothly moving cabin that could tell you whether you were still or gliding forward at constant speed. Motion, in that sense, was already relative. You could say the ship moved past the shore, or the shore moved past the ship. What mattered was the relationship between them. That insight did not overthrow Newton. It fit comfortably inside the Newtonian world, but it planted a seed. It suggested that nature did not always reveal an absolute state of motion. Some things depended on perspective, on where one stood, on how one moved. For everyday life, this caused no trouble at all. Carriages rolled, stars turned overhead, and clocks ticked on. But once that small idea took root, that motion might be known only in relation to something else. The ground had shifted ever so slightly. The old universe still appeared solid, but somewhere within it a door had opened. By the 19th century, the old universe had become even more impressive. Physicists had explained heat more carefully, traced electricity and magnetism with growing precision, and built a picture of nature that seemed to be knitting together beautifully. Then light, which had long seemed almost too familiar to be mysterious, began to ask more of them. For most of human history, light was simply what allowed the world to be seen. It revealed mountains at dawn, turned dust into gold in a window, and brought the stars into the night like tiny punctures in a dark curtain. But science had gradually learned that light was also a physical phenomenon, something with properties that could be measured and described. One of the great steps came from James Clerk Maxwell, who showed that electricity and magnetism were not separate curiosities, but two aspects of the same field. His equations implied that disturbances in this electromagnetic field would move through space as waves, and those waves traveled at a definite speed. That speed matched what people had measured for light. The conclusion was extraordinary. Light itself was an electromagnetic wave. This was elegant, but it also raised a problem. Waves, as people understood them, usually belonged to some medium. Sound moved through air. Ripples moved through water. Vibrations moved through strings or metal. If light was a wave, then what exactly was waving? The answer many scientists favored was a hypothetical substance called the luminiferous ether. It was imagined as an invisible medium filling all of space, delicate enough not to slow the planets, yet substantial enough to carry light from star to eye. The idea may sound strange now, but at the time it was a reasonable attempt to preserve familiar intuitions. Waves seemed to require something to wave in, and once the ether was imagined, another question followed naturally. If Earth moved through this invisible medium as it traveled around the sun, then should there not be a kind of ether wind? Should light not seem to move slightly differently depending on whether Earth was moving into that wind or across it? The expected effect was tiny, but not impossible to measure. There is something tender in the patience of such questions. Nature rarely announces its deepest truths with trumpets. More often, it waits in fine discrepancies, in numbers that come back just a little wrong, in assumptions tested so carefully that even silence begins to speak. That was where physics had arrived. Newton's world still stood, Maxwell's vision had deepened it, and light had become illumination and messenger at once. If it was truly a wave, the ether seemed to offer a home for it. Yet that invisible home was still only an idea. Soon, two experimenters would go looking for Earth's motion through that silent medium. And what they did not find would matter far more than what they did. In 1887, Albert A. Michelson and Edward Morley carried out one of the most famous experiments in science. Their goal was not to destroy the old picture of reality. They hoped to detect Earth's motion through the ether and strengthen the existing framework. The basic idea was delicate but ingenious. If Earth were moving through the ether, then light traveling in the direction of that motion should take slightly longer than light traveling across it, just as a swimmer moving against a current behaves differently from one crossing it sideways. The difference would be extraordinarily small, but Michelson had designed an instrument subtle enough to search for it. That instrument, called an interferometer, split a beam of light into two parts and sent them along different paths, then brought them back together. If one path took even a tiny bit longer than the other, the recombined light would shift its interference pattern. It was a way of turning an almost imperceptible difference into something visible. They performed the experiment with great care. The apparatus could be rotated, allowing them to compare different directions of motion. As Earth moved through space, the hoped-for effect should have changed with orientation. A subtle drift in the light pattern should have appeared. But the drift did not come. The result was close to null. Not dramatic, but far more unsettling than a loud contradiction. Again and again, the expected signature of Earth's motion through the ether refused to show itself. The invisible medium that had seemed so natural and useful remained hidden. At first, many scientists tried to save the old picture. Perhaps the apparatus had contracted slightly as it moved through the ether. Perhaps matter behaved oddly in motion. Perhaps the ether itself was more elusive than anyone had guessed. These were not foolish responses. They were signs of how deeply established ideas can shape the imagination. Among those attempts was the proposal later associated with Hendrik Lorentz and George Fitzgerald that objects moving through the ether might shrink slightly in the direction of motion. It was a clever patch, but it also carried a faint scent of strain. The theory was being asked to bend in order to preserve something no one had actually observed. This is one of the quiet beauties of science. It does not move forward only by brilliant declarations. Sometimes it advances through discomfort, through the long, patient moment when a trusted picture stops fitting quite as well as it once did. By the end of the 19th century, physics was suspended in that moment. Newton still worked, Maxwell still worked, daily life still worked, and yet the ether, expected by so many, seemed unwilling to leave a trace. The stage was set for a different kind of question. Not, how can the ether be saved? But, what if the need for it had been misunderstood from the beginning? In 1905, a young Albert Einstein published a paper with a title calmer than its consequences. He was working in a patent office in Bern, and he approached the growing tension in physics with simplicity. Instead of adding new machinery to rescue the picture, he asked what would happen if one took two ideas seriously at the same time. The first idea was inherited from Galileo. The laws of physics should look the same for all observers moving at constant speed relative to one another. If you were in a smoothly moving train and someone else stood on the station platform, neither of you should be able to claim a special state of rest simply from the behavior of nature. The second idea was stranger. The speed of light in empty space should be the same for all such observers, regardless of how the source of light or the observer was moving. This was the daring step. It asked people to stop trying to explain light by reference to an ether wind and instead accept what experiments seemed to be whispering. At first glance, these two statements seem innocent enough, but together they place pressure on the Newtonian assumptions. If the laws of physics are the same in all uniformly moving frames, and the speed of light is the same in all of them, then something else must give way. Something once taken as fixed must become flexible. Einstein's genius was conceptual. He was willing to let go of an older intuition in order to preserve a deeper consistency in nature. He did not begin by declaring that time changes. He began by trusting the principles and following them wherever they led. Imagine a flash of light emitted inside a moving train. To someone riding the train, the light spreads outward in all directions at its usual speed. But to someone watching from the platform, the train itself is moving. Under common sense, one might expect the light speed to combine with the train's motion, yet Einstein's new framework says no. The platform observer measures the same speed of light. How can that be? The answer, though still ahead of us, is that measurements of time and space must adjust. Distances that seem straightforward in one frame are not quite the same in another. Moments that seem simultaneous in one place are not perfectly shared in another. The fault is not in the clocks or rulers. The fault is in the old assumption that clocks and rulers were universal in the first place. This was the opening move of special relativity. Special because it dealt with a special case. Motion at constant velocity, without gravity. Even within that setting, it transformed the architecture of reality. And so, the revolution began. No ether, no absolute rest, no single cosmic clock keeping identical time for every corner of the world. Only observers, light, motion, and a universe more subtle than anyone had imagined. From here, the strangeness would deepen, but so would the beauty. The first great consequence of Einstein's new picture can be approached with an object that exists mostly in imagination, though it helps reveal something real. Physicists sometimes describe a simple clock made not of gears or springs, but of light. Picture two small mirrors facing one another with a pulse of light bouncing gently up and down between them. Each round trip marks a tick. To the person holding this clock still in their own frame of motion, the arrangement seems almost childishly simple. The light moves straight upward, then straight downward, and the clock ticks with perfect regularity. But now imagine that this same light clock is carried aboard a train moving smoothly through the night. To someone on the train, nothing has changed. The beam still rises and falls between the mirrors. The tick remains the same. To someone standing outside, though, watching the train glide past, the story looks different. The clock is moving sideways while the light travels between the mirrors. So the beam no longer traces a simple vertical path. Instead, it follows a diagonal route, like a tiny shining zigzag, because while the light is climbing upward, the entire clock is also moving forward. And here the quiet tension appears. Light must still travel at the same speed for both observers. That is Einstein's starting point. But if the outside observer sees the light follow a longer diagonal path, and if light speed has not changed, then the journey must take more time. The tick of the moving clock stretches. This is time dilation. A moving clock runs more slowly relative to an observer who sees it in motion. Not because the mechanism is damaged, not because the observer is confused, but because time itself is not universal. Duration depends in part on motion. The idea can feel slippery at first because we do not notice it in ordinary life. On a train, in a car, in an aircraft, our clocks do not seem to misbehave. But that is only because our speeds are tiny compared with the speed of light. In the quiet middle world of daily human experience, relativity hides almost completely. Its effects are real, yet so small that Newton's older approximation remains wonderfully useful. Still, the principle is there, woven into reality. If two identical clocks begin together and one journeys at enormous speed while the other remains behind, they will not fully agree when reunited. One will have lived through slightly less time. This was not fantasy. It would later be tested with fast-moving particles with exquisitely precise atomic clocks, even with clocks flown on aircraft and compared with those on the ground. Again and again, the universe answered in the same soft voice. Time does not pass in quite the same way for everyone. What seemed once like the most stable backdrop of existence had begun to move beneath our feet. If time can stretch, then space cannot remain untouched. The two had long been treated as separate, almost like neighboring kingdoms with clear borders between them. One contained positions and distances, the other contained moments and durations. But under relativity, that border begins to blur. A change in motion reaches into both. Imagine again that smooth train crossing the dark countryside, and imagine someone inside measuring the length of a carriage with a careful ruler. For the passenger, the carriage is at rest. Its length is ordinary, familiar, and stable. But to an observer standing beside the track, the carriage is moving at great speed. If light keeps the same speed for both observers, then distance itself must join the adjustment. The result is called length contraction. An object moving relative to an observer is measured to be slightly shorter in the direction of motion than it is in its own rest frame. The faster it moves, the greater the contraction becomes. Once again, nothing is broken. No metal has buckled. The shortening belongs to the structure of measurement itself. This can sound like a trick of perspective, but relativity is more demanding than that. It is not merely that things look shorter, as faraway mountains or receding roads look smaller to the eye. Rather, space is being measured differently because time is being measured differently too. The old certainty that everyone shares one grid of lengths and one river of time has quietly dissolved. It helps to remember how extreme the conditions must be before this becomes noticeable. A bicycle, a ship, even a jetliner do not contract in any way that human senses could detect. Only when speeds approach that of light do these differences rise into significance. Then the universe begins to reveal that its deepest rules are not built to match our everyday intuitions. There is something almost merciful in that concealment. We live our lives in a slow province of the cosmos, where the world seems steady and simple enough for habit and memory. Yet beneath that calm surface lies a more subtle order, waiting for those who look closely enough. In modern particle accelerators, objects moving near light speed behave in precisely these ways. Their lifetimes, energies, and paths make sense only if time and length have shifted as relativity says they must. Nature does not treat this as poetry. It treats it as law. So now the old picture has changed again. Moving clocks slow. Moving lengths shrink. Neither observer is privileged, and neither has stepped outside reality. Each measures faithfully from within their own motion. The universe remains lawful, but its lawfulness has become stranger and more graceful than the old mechanical dream allowed. And still, an even deeper surprise is waiting. It concerns not motion or distance alone, but the question of whether two events can truly happen at the same time. Among all the ideas in special relativity, the one that most quietly unsettles the mind may be the loss of universal simultaneity. We are so used to speaking of now, of imagining that this moment spreads evenly across the world, that it feels almost unnatural to question it. And yet relativity does. Picture a very long train moving swiftly through the night. Imagine that lightning strikes both ends of the train at what seems to be the same instant. An observer standing on the embankment, exactly midway between the two strikes, sees the flashes arrive together and concludes that the strikes were simultaneous. Equal distance, equal travel time, equal arrival. Now place another observer at the midpoint inside the moving train. Because the train is advancing toward one flash and away from the other, that observer meets the frontward flash sooner and the rearward flash later. Since light travels at the same speed in both directions, the observer on the train concludes that the strikes did not happen at the same time. One occurred earlier than the other. Neither observer is making a mistake. They disagree because simultaneity itself depends on the state of motion of the observer. Events that are simultaneous in one frame need not be simultaneous in another. This is where relativity becomes more than a set of odd corrections applied to moving clocks and rulers. It becomes a new architecture of reality. The universe is not divided into one absolute present shared by all beings in all places. Instead, each observer carries a version of time braided with their motion through space. The idea can feel lonely at first, as though it removes some hidden communal thread from existence. But it also carries a quiet dignity. Reality does not arrange itself around human preference. It does not promise that our instinctive picture of now will survive close examination. What it offers instead is consistency at a deeper level, where the speed of light and the laws of physics remain steadfast even as old assumptions fall away. From this new view, time is no longer a single universal river flowing identically for every shore. It becomes more like a landscape of paths, each observer tracing a route with their own ordering of events. There are still causes and effects, still structure and law, but the great shared clock of Newton has faded. When Einstein later joined space and time into a single framework, this strange lesson became easier to express. Different observers carve reality into moments and distances differently, because space and time belong together. And so the revolution deepens. Not only do clocks stretch and lengths contract, even the simple phrase "at the same time" must be handled with care. The universe has not become chaotic. It has become more exact, and in doing so, more subtle than common sense first imagined. By this point, space and time no longer resemble the separate absolutes that earlier centuries had trusted. They bend toward one another, exchanging certainty, and from that exchange, a new picture slowly emerges. In the years after Einstein's 1905 paper, the mathematician Hermann Minkowski gave that picture a powerful form. He suggested that space and time are not truly independent at all, but part of a single union, space-time. The word itself sounds modern, almost architectural, yet the idea can be held gently. Every event in the universe happens somewhere and somewhen. A candle is lit in a room at a certain hour. A star releases light in a distant galaxy millions of years ago. A hand reaches across a pillow just before sleep. Position and moment are never separate in reality, only in habit. Minkowski's insight was to say that physics should treat them as parts of one fabric. This does not mean space-time is a cloth in any literal sense, nor a mystical fog filling the heavens. It is a geometric way of describing the structure within which events occur. Different observers, moving differently, slice that structure into time and distance in different ways. What one calls more time and less distance, another may call less time and more distance. Yet beneath those differences lies a deeper invariance, a kind of quiet agreement. That shared quantity is sometimes called the space-time interval. We need not dwell on its mathematics tonight. What matters is the idea that while observers may disagree on lengths, durations, and simultaneity, there remains a more fundamental relationship that all of them preserve. Relativity did not replace order with disorder. It found a more durable order beneath appearances. There is comfort in that. At first, relativity can seem like a story of things being taken away. Absolute rest, universal time, a common present. But what it really offers is refinement. It asks us to trade a coarse certainty for a subtler truth. The world is not less intelligible than before, it is more carefully made. Once space-time enters the story, the earlier effects begin to feel less like isolated curiosities and more like shadows cast by a single underlying geometry. Time dilation is not one strange trick. Length contraction is not another separate trick. They are different expressions of the same deeper structure. Physicists came to picture each object as tracing a path through space-time, a kind of world line. A planet looping around the sun, a photon crossing the dark, a person walking from childhood to old age, all leave their own trajectories in this four-dimensional account. We do not see these lines with our eyes, yet they help reveal how motion and time belong together. And hidden within this new framework was another remarkable possibility. If mass and motion behave differently than once believed, perhaps matter and energy were not as separate as they seemed either. The equation is brief enough to fit in a margin, yet it altered how humanity understood the substance of the world. I equals EIMC squared. It is often treated as a symbol of genius itself, but beneath its fame lies a simple statement. Mass and energy are deeply related. Matter is, in a sense, concentrated energy. To see why this belongs within relativity, we need only remember that motion, time, and measurement were already being rewritten. If an object's behavior changes with speed, and if energy is tied to motion, then the old boundaries between matter and energy begin to soften. Einstein showed that even a body at rest possesses an energy simply by virtue of having mass. The amount is enormous because it is multiplied by the speed of light squared, and that number is vast. This does not mean that stones, teacups, or sleeping cats are secretly exploding with visible force. Most matter sits peacefully in its form, and converting mass into usable energy is not easy. Yet the principle is real. In the sun, tiny losses of mass become radiant energy that warms planets and feeds oceans, forests, and skin. In radioactive decay and nuclear reactions, the same relation reveals itself more dramatically. Matter and energy can exchange identities. Here again, relativity offered not fantasy, but a truer accounting. The universe held deeper reserves than Newtonian intuition had guessed. Mass was not merely the measure of how much stuff something contained. It was bound to energy, inertia, and motion in ways that linked the smallest particle with the brightest star. The equation also carried a moral weight once technology caught up to it. Human beings learned to release the energy hidden in matter with terrible violence, and also with quieter purposes, from medical treatments to power generation. Like many deep truths, it was not gentle merely because it was elegant. Still, in the context of our quiet journey tonight, the deeper wonder lies elsewhere. It lies in how an equation so compact could arise from questions about time, light, and motion. Relativity was not born as a hunt for power. It began as a patient attempt to understand why light behaved as it did and what that behavior implied about reality. By now, the old universe of fixed space and universal time has transformed almost completely. Motion changes duration. Distance depends on the observer. Simultaneity phrase. Space and time unite into spacetime. Mass and energy lean toward one another as kindred things, yet one great force still stands partly outside the picture we have built. Gravity remains. Special relativity describes a world of constant motion without the complications of acceleration and falling. But the real universe contains stars, planets, weight, and descent. To carry relativity farther, Einstein would have to ask an even quieter question. What exactly is gravity if space and time themselves are no longer what we thought? Gravity had always felt personal. Long before anyone wrote equations, people knew the sensation of being pulled downward the way a dropped object returned to Earth without argument. Newton gave this experience a majestic form. He described gravity as a force acting across distance, binding apples to orchards, moons to planets, and planets to the sun. His law worked so well that it could guide cannonballs and eclipses alike, and yet there was something slightly mysterious in it. Newton understood this. His formula described how gravity behaved, but it did not fully explain what gravity was. How could one body act upon another across empty space? The sun seemed somehow to reach across the void and tug the earth into its path. It was effective, predictive, and mathematically beautiful. Yet the mechanism remained hidden. For many years, this was not an urgent problem. Physics often advances by learning how before it learns why. If a law predicts the world faithfully, people are content to live beside its unanswered questions for a time. But once Einstein had reimagined space and time, gravity could no longer remain untouched. Special relativity had removed instant action as an easy possibility, because no signal and no influence should outrun light. So the old picture began to feel incomplete. If the sun were somehow moved, could its effect on Earth change instantly? Relativity suggested no. Something deeper had to be carrying the story. Gravity could not simply be a silent pull passing across a fixed stage, because the stage itself, space and time together, was no longer fixed. Einstein began to search for a new way of thinking. And as so often happens in science, the next step did not arrive first as a complicated equation, but as an image. It was an image so simple that one could hold it in the mind half asleep. Imagine a person sealed inside a small elevator. If the elevator is resting on Earth, the person feels weight in the usual way. Their feet press into the floor. A dropped coin falls downward. Everything feels ordinary. But now imagine that same elevator far out in empty space, accelerating upward. Their feet again press into the floor. A dropped coin again falls toward them. From inside the cabin alone, the two situations begin to resemble one another. That resemblance became one of Einstein's deepest clues. Perhaps gravity and acceleration were not separate things after all, but two expressions of a more hidden unity. Perhaps the feeling of weight on Earth and the feeling inside an accelerating cabin were, in some profound sense, locally equivalent. This was not yet general relativity, but it was the doorway to it. The force once treated as the most familiar of all was becoming strange again, though not in a chaotic way. It was being invited into the same quiet revolution that had already transformed time, space, and light. Einstein followed the elevator, thought a little farther, and the consequences grew quieter and deeper. If standing in a gravitational field can feel like accelerating, then perhaps gravity does more than pull. Perhaps it also changes how light behaves, how clocks run, and how motion is experienced from place to place. Consider again the sealed elevator in empty space, now accelerating upward. Imagine a beam of light entering through a tiny hole in one wall and traveling straight across toward the opposite side. To someone outside, the light moves in a straight line while the elevator rises beneath it. But to the person inside, the beam does not seem perfectly straight. During the light's crossing, the cabin has moved upward, so the beam appears to bend slightly downward before it reaches the far wall. If acceleration can make light appear to curve, and if gravity is locally equivalent to acceleration, then gravity should also bend light. That was a breathtaking thought. In the old Newtonian imagination, gravity acted most naturally on things with mass, on stones and planets and falling bodies. But now, even light, massless and swift, seemed destined to feel gravity's influence. The same elevator reveals something else. Suppose a flash of light is sent from the floor upward to the ceiling. If the elevator is accelerating upward, the ceiling is moving away from the light while the beam climbs. To the observer above, the light is received a little differently than it was emitted below. In relativity language, its frequency shifts. The effect is tiny, but it suggests that gravity should alter light not only by bending its path, but by changing its color, more precisely its energy. And hidden within that is a quiet lesson about time. Frequency is tied to rhythm. Rhythm is tied to clocks. If light shifts as it moves through a gravitational field, then clocks at different heights in that field cannot be running in exactly the same way. Time itself must pass differently depending on gravity, just as it passes differently depending on motion. This was one of Einstein's great gifts. He could sit with a simple image long enough for its implications to bloom. A person in an elevator, a light beam crossing a cabin, a flash sent from floor to ceiling. From such quiet mental pictures came changes in our understanding of the cosmos. The familiar world began to soften again. Weight was no longer merely a pull downward. It became entangled with acceleration, with light, with the pace of time. The floor underfoot, the beam in the air, the ticking of a clock on a shelf, all belonged to the same story. And yet the step had not fully arrived. If gravity could bend light and change time, then perhaps gravity was not a force in the ordinary sense at all. Perhaps objects were not being pulled through space. Perhaps space and time themselves were being shaped, and everything else was simply following the shape. The picture often used to introduce general relativity is the image of a heavy ball on a stretched sheet, with smaller balls rolling inward along the dip. It is not perfect, and if pressed too literally, it can mislead, but it helps the sleeping mind approach something otherwise difficult to picture. Mass tells spacetime how to curve, and curved spacetime tells matter how to move. That sentence became famous because within it lies a transformation as profound as anything in science. In Newton's account, gravity is a force between bodies. In Einstein's mature view, gravity is geometry. Planets are not being tugged through a passive emptiness by invisible strings. They are following the natural paths available within a curved space-time shaped by mass and energy. A useful word here is geodesic. On a globe, the shortest route between two places is not a flat line on a paper map, but a great circle traced on the curved surface itself. Aircraft flying long distances follow such routes whether passengers think about the geometry or not. In a similar way, objects in space-time follow the straightest paths available to them within curvature. What we experience as gravity is often just this quiet obedience to geometry. This is why free fall becomes so interesting. A person falling, if we could ignore the air and the danger, would briefly feel weightless. An astronaut orbiting Earth also feels weightless. though Earth still holds the orbit in place. In Einstein's account, these are not paradoxes. The falling body and the orbiting astronaut are following natural paths through curved spacetime. What feels like gravity most strongly is often not free fall itself, but the interruption of free fall by a floor, a chair, or the ground beneath our feet. That is such a strange reversal. The sensation of weight, once taken as direct evidence of gravity's pull, becomes evidence that something is preventing our natural motion. We stand on Earth because the ground keeps redirecting us away from the geodesic we would otherwise follow. The sun, then, does not cast an invisible hook that drags the planets around. It shapes the geometry around it, and the planets move within that shaped geometry. Light from distant stars also passes through this terrain, and its path bends accordingly. Time near a massive body slows relative to time farther away. Space is not a blank container. It participates. When Einstein completed the field equations of general relativity in 1915, he had found a way to express this relationship mathematically with great power. We need not enter those equations tonight. It is enough to feel the conceptual shift. Reality is not a stage with actors moving upon it. The stage itself can curve, deepen, and influence the drama. And once that was understood, the heavens no longer seemed merely occupied by planets and stars. They became expressions of space-time shape, bending light and time together in the dark. A theory this bold could not remain a beautiful idea alone. It had to meet the sky and survive. Einstein knew that a new picture of gravity would matter only if nature consented to it, and so general relativity soon faced a series of quiet tests. One of the first concerned Mercury, the innermost planet. For years, astronomers had noticed that Mercury's orbit did not behave exactly as Newton's laws predicted. Its elliptical path slowly rotated, and most of that motion could be explained by the influence of the other planets. But a small leftover piece remained, a discrepancy that would not disappear. Einstein's new equations accounted for that extra precession naturally. It was one of the first signs that he had touched something real. Then there was light. If gravity is curvature, starlight passing near the sun should bend. This could not easily be observed in ordinary daylight, because the sun's brilliance hides the nearby stars. But during a total solar eclipse, when the moon covers the sun's face, those stars briefly emerge. In 1919, expeditions led by Arthur Eddington and others photographed stars near an eclipsed sun and compared their apparent positions with images taken when the sun was elsewhere. The reported shift matched Einstein's prediction closely enough to electrify the world. Yet behind the headlines lay something quieter and more enduring. Light itself had appeared to follow the curvature of space-time. The old intuition that only heavy matter could feel gravity was falling away. As the decades passed, the evidence deepened. More careful measurements of light deflection, radar signals passing near the sun, and the timing of clocks all reinforced the same picture. Gravity changes not only trajectories, but time itself. A clock closer to a massive body runs more slowly than one farther away. This phenomenon, called gravitational time dilation, is tiny on human scales, but it is not optional. The universe insists on it. There is something lovely in that insistence. General relativity is often spoken of as difficult, yet nature performs it effortlessly. Light bends. Clocks drift by different amounts. Planets trace paths not because they have read Einstein, but because geometry has already written the rule. A scientific theory becomes trustworthy not because it is admired, but because it continues to survive contact with reality. General relativity has done that with unusual grace. It began as a daring act of thought and matured into one of the most precisely tested frameworks in physics. By now, the old world of fixed space, fixed time, and instantaneous pull had receded far into the background. In its place stood a quieter and more elastic universe, one in which geometry itself kept the deepest account. By the early 21st century, relativity had become something both grand and oddly ordinary. It remained one of the deepest descriptions of the universe ever written, reaching outward toward stars, black holes, and the history of the cosmos. And yet its effects had also entered daily life so quietly that many people use them without noticing. A good example circles above us. The satellites that make global positioning possible carry precise atomic clocks. They move swiftly around Earth, so special relativity tells us their clocks should tick a little more slowly than clocks on the ground. But they are also farther from Earth's mass, where gravity is weaker, so general relativity tells us their clocks should tick a little more quickly. Both effects are real, and they do not cancel exactly. Engineers must account for them continuously. If they did not, a navigation system would drift badly. There is something almost tender in that fact. A driver seeking a street, a ship finding a harbor, a phone locating a nearby cafe, all depend in part on the truth that time is not identical everywhere. Einstein's ideas, born from thought experiments about trains, light, and elevators, now whisper inside devices held in the palm of the hand. At larger scales, relativity opens still grander doors. It helps explain the behavior of neutron stars, the collapse of matter into black holes, and the expansion of the universe itself. Under Einstein's equations, space-time is not merely a backdrop for cosmic events. It can evolve, stretch, ripple, and in extreme circumstances, fold into regions from which not even light can escape. Black holes, once almost unthinkable, emerged naturally from the theory. They are not holes in the ordinary sense, but regions where curvature becomes so severe that the paths leading outward all turn inward instead. Astronomers now find their signatures in the motions of stars, in hot disks of infalling gas, and in the shadows they cast against surrounding light. Relativity also suggested that violent cosmic motions should send faint ripples through space-time itself, like tremors crossing a dark lake. These gravitational waves were predicted long before they were measured directly, and for decades they remained one of the theory's most elegant promises. Their eventual detection would become one of modern science's most moving confirmations, a moment we will drift toward a little later. For now, it is enough to notice how the theory lives on many scales at once. It governs the practical and the immense, the subtle correction in a satellite clock, and the deep architecture of galaxies. Few ideas in science have joined intimacy and vastness so completely. And as the night story continues, relativity will lead us farther into those remote regions, toward black holes, cosmic history, and the realization that the universe is not rigid beneath us, but supple, curved, and alive with time. Relativity had one more whisper to offer before the story could settle. If gravity is not a force traveling through empty space, but a change in the shape of space-time itself, then violent motions in the cosmos should not remain perfectly still in their effects. When massive bodies accelerate, especially in pairs, the geometry around them should tremble. Not loudly, not like thunder rolling through the sky, but as a faint ripple moving outward at the speed of light. Einstein predicted these ripples in 1916. They came to be called gravitational waves. The phrase sounds dramatic, yet the reality is extraordinarily delicate. A wave passing through Earth does not toss buildings or stir oceans. It changes distance by an amount so small that for generations it seemed almost impossible that human beings would ever detect it. A gravitational wave stretches space in one direction and compresses it in another, then lets it relax again, like a breath passing through the fabric of measurement itself. To sense such a thing, one must listen not with ears, but with astonishing patience. Decades after Einstein's prediction, scientists built observatories with long vacuum tunnels and laser beams sent back and forth between mirrors. If a gravitational wave passed, the lengths of those tunnels would alter by a fraction so tiny it scarcely seems readable. And yet the instruments were refined until even such faint changes could, in principle, be noticed. Then, at last, in 2015, the signal came. Two enormous black holes far away and long ago had spiraled inward around one another, collided, and become one. In that final dance, they sent a pulse across the universe, a ripple in space-time that crossed unimaginable distances before brushing the Earth. When the detectors known as LIGO measured it, humanity had done something quietly extraordinary. We had not merely seen the universe, we had felt its geometry quiver. There is something deeply SleepWise about that idea. The cosmos is not silent, but softly resonant. Great events occur in darkness, and their passage reaches us not always as light, but as subtle changes in distance, rhythm, and form. Relativity had predicted that space-time itself could carry news, and the universe had answered yes. For our purposes tonight, the technical triumph is less important than the mood it leaves behind. The world Einstein described is not static or rigid. It can bend around stars, slow clocks near planets, guide light around the sun and also ring faintly when massive things collide. Space-time is not a passive emptiness. It has structure, and in extreme moments, that structure can ripple. So the theory that began with trains, light beams, and uncertain simultaneity has carried us all the way to a new kind of cosmic listening. Not bad for a quiet question about whether light behaves the same for everyone. If gravitational waves revealed space-time trembling, black holes revealed what happens when curvature grows severe beyond ordinary imagination. They have become familiar figures in modern culture, yet the original idea emerged not from fantasy, but from the mathematics of general relativity. If enough mass is compressed into a small enough region, space-time can curve so deeply that every path leading outward bends back in. Light itself cannot escape. That is the basic meaning of a black hole. It is not a hole punched through the universe, nor a cosmic drain swallowing everything indiscriminately. It is a region bounded by what physicists call an event horizon, a kind of one-way boundary. Cross that edge, and all future directed paths point inward. Nothing is seen climbing back out, because the geometry no longer permits outward return. This sounds violent, but from far away, black holes can also be strangely quiet. A black hole with the same mass as the sun would still guide nearby objects by gravity in a perfectly lawful way. If the sun were somehow replaced by such a thing without changing its mass, the planets would continue in their orbits, though of course the warmth and light that sustain life would be gone. The terror people often imagine belongs less to black holes themselves than to the extreme environments near them. Around many black holes, matter forms hot swirling disks, glowing fiercely as it falls inward. Friction and compression heat the gas until it shines across the electromagnetic spectrum. In some galaxies, enormous black holes sit at the centers, feeding slowly or sometimes violently, launching jets across intergalactic space. These are among the most energetic sights in the known universe. Yet the strange heart of the matter remains geometric. Black holes are not monsters added to the cosmos. They are among the natural consequences of curved space-time. There is also a gentler way to think about them. A black hole marks a place where our ordinary intuitions stop traveling well. Clocks far away and clocks near the horizon disagree dramatically. To a distant observer, processes near the edge seem slowed, reddened, stretched. Time itself participates in the descent. Black holes are places where relativity becomes visible in its most concentrated form, where time and geometry reveal how inseparable they truly are. In recent years, astronomers have even produced images of black holes, or rather, of the glowing matter around them and the dark shadow against that light. To glimpse such an image is to see theory made tangible, not a literal photograph of emptiness, but evidence of curvature on a scale so great that it leaves a silhouette against the universe. And still, even black holes do not stand outside the order of relativity. They are not exceptions to the theory. They are reminders of how far the theory reaches when matter gathers, light bends, and time leans into darkness. Relativity did not stop at stars, clocks, and black holes. Once Einstein provided a new description of gravity, his equations could also be turned toward the universe as a whole. And when they were, a surprising possibility emerged. The cosmos might not be fixed and eternal in the old static sense. Space itself might change over time. This was a difficult thought, even for Einstein. Many people of his era preferred to imagine the universe as unchanging on the largest scales, stable in its broad arrangement, even if local events came and went. Einstein initially adjusted his equations by adding what is now called the cosmological constant, partly to allow a static universe. It was an understandable move. The human mind often reaches first for stillness, but the equations were less attached to stillness than the imagination was. Other physicists, among them Alexander Friedman and Georges Lemaitre, explored solutions in which the cosmos could expand or contract. Then astronomy began to catch up. Observations by Edwin Hubble and others showed that distant galaxies are, in general, moving away from us, and the farther they are, the faster they recede. This was not because we occupy a privileged central place, but because space itself is stretching, carrying galaxies apart. This is one of relativity's most beautiful enlargements of perspective. The universe is not simply populated by objects moving through an unchanged backdrop. The backdrop itself participates. Space can expand. The fabric of spacetime, introduced first to describe gravity, becomes the stage of cosmic history. From this came the modern picture of an evolving universe with a hot, dense early state, what later generations would call the Big Bang. The phrase can sound explosive, but it is better imagined as the expansion of space from conditions far hotter and denser than those we know now. Relativity does not merely describe the local dance of planets. It helps tell the story of how the visible cosmos changed over billions of years, and the story is still unfolding. Observations suggest not only that the universe expands, but that its expansion is now accelerating, apparently influenced by some still mysterious component often gathered under the name dark energy. Once again, relativity provides the framework even when the full cast of cosmic actors is not yet understood. There is a quiet lesson in all this. The theory that began with the speed of light and the relativity of simultaneity grew into a description of cosmic history itself. It reached from the small discrepancy in Mercury's orbit to the widening between galaxies, from clocks on Earth to the shape of the whole universe. And yet, for all that scale, relativity never really leaves the intimate. It still returns to the same soft truths. Where you are matters, how you move matters, gravity changes time, and the universe is more fluid and relational than it first appears. After all this, it can be tempting to think of relativity as a theory belonging only to extremes. It seems to live among fast particles, black holes, satellite clocks, and the deep mathematics of cosmology. And in one sense, that is true. Most of the time, ordinary life unfolds in the slow middle ground where Newton's older picture works well enough to guide feet, furniture, weather, and seasons. But relativity matters even when it remains hidden. It changed not only equations, but habits of thought. Before Einstein, people often imagined the world as built from separate pieces. Space here, time there, matter over there, gravity acting between them from the outside. After relativity, those divisions grew more porous. Motion affects time. Gravity shapes geometry. Matter and energy belong to one another. The world becomes less like a machine assembled from rigid parts and more like a woven structure whose elements make sense only in relation. That is why the theory has remained so influential even beyond physics. It did not teach that everything is subjective, as the word relativity is sometimes carelessly used in everyday speech. Einstein's theory is not a philosophy of anything goes. In fact, it is stricter than that. It says that different observers may measure differently, but their measurements are linked by deeper rules. Relativity loosens naive certainty only to reveal a more faithful order underneath. There is something quietly comforting in this. The universe is not arranged around a single privileged viewpoint. No observer gets to stand outside reality and judge it from nowhere. Each perspective is partial, situated, and real. Yet the cosmos remains lawful. Truth is not destroyed by differing viewpoints. It is refined by understanding how those viewpoints fit together. Perhaps that is one reason relativity still feels so modern. It honors relationship without abandoning structure. It makes room for difference without surrendering coherence. It reminds us that where we stand matters, but also that the world is not arbitrary. And then there is the softer emotional effect. Once you have spent a little time with relativity, the night sky feels different. The stars are no longer fixed jewels hanging above a universal clock. They belong to a dynamic fabric in which light travels finitely, gravity bends paths, and time itself has texture. Looking up becomes a gentler kind of wonder, not more frightening, only more spacious. The clock on a bedside table still ticks in its familiar way. The room still darkens. The body still grows heavy with sleep. Yet hidden beneath that ordinary calm is a universe in which every tick belongs to a local rhythm. Every beam of light travels through curved geometry, and every quiet moment takes its place within space-time. The world has not become less solid. It has become more subtle. And often, when things grow more subtle, they also grow more beautiful. So now, the journey can grow quiet. We began with a world that seemed steady and unquestioned. Time flowed evenly, Space waited like a silent stage, and gravity reached across emptiness with dependable force. But then light asked a more delicate question. Experiments listened. Einstein followed the question with unusual courage, and little by little, the universe loosened. Time ceased to be universal. Space gave up its rigid certainty. Simultaneity, once assumed to be obvious, became something local and observer-bound. Mass and energy leaned together. Gravity changed from a pull into a curvature. Space-time bent around stars, rippled under collisions, and expanded across the history of the cosmos. What had seemed like separate features of reality became aspects of one deeper arrangement. And yet, the strangest part is how gentle this revolution feels when approached slowly. Relativity is often introduced as something difficult or intimidating, as if it belongs only to geniuses, laboratories, and severe concentration. But beneath the equations, it is also a lesson in humility and tenderness. Nature was never obliged to match our first intuitions. The universe did not have to grant us one shared clock or one fixed stage. Instead, it offered something subtler, and in its subtlety, something strangely graceful. Tonight, perhaps that is the feeling to keep. Not the technicalities, not the terminology, not the exact order of every experiment and proof, but the mood of it, the sense that reality is more relational than rigid, that motion and time are braided, that gravity is not merely a downward pull, but a shaping of the paths things can take, that even light, the ancient companion of waking and dreaming, follows rules more elegant than anyone once knew. Outside the room, the earth turns through space-time without your noticing. The planet curves around the sun moves within the galaxy. The galaxy drifts among countless others. Somewhere very far away, light is crossing dark distances. Somewhere else, two dense objects may be orbiting one another, sending faint ripples across the cosmic fabric. And here, in the small shelter of a night routine, your own local clock continues its soft measure. This is one of the quiet gifts of science. It enlarges the world without making home feel smaller. It tells us that the universe is vast, curved, and astonishing, and still leaves room for blankets, lamp glow, breath, and rest. So let the clocks continue their little ticking. Let the stars keep their patient distances. Let space curve where it must, and let time pass in its own local way. You do not need to solve the universe tonight. You only need to drift within it, held for a little while by gravity, darkness, and the soft intelligence of a world more mysterious than it first appeared. The world slows, and so do we. Good night.